Okay, yeah, thank you. And there is a prize for asking questions, so I mean, okay, good. Also, some people wanted me to, not put down blackboards too soon before you take notes. But again, in the book, there are all formulas you need. So, of course, you're welcome. When you write down something, it's a better way to remember and understand. But sometimes it's just pays to put your pen down, to look at me and try to, ask questions, understand it. Don't worry about details of the formulas. They're all written down in the book. More worry about understanding what the hell is going on, right? Because that's what all these lectures about. So as in any series, I start from a reminding of the previous episode, okay? So what we've ended, I remind you that we derive the equations for ideal fluid. Ideal means that there are only normal forces inside. There was a condition of being ideal. It means many things. Then we further considered simplification, assuming that it was uniformly heated, not a uniform temperature fluid, which means isentropic. And then we further made an assumption that the beginning of times our flow was potential. Then within this equation, it stays potential because there is no friction forces which would produce vorticity. And then in this simplest setting, we solved the simplest problem, the motion of a sphere in an infinite uniform fluid. And for this, of a sphere moving with a velocity u, having radius r, because it's a potential flow for which velocity is a gradient of potential, the potential was r cubed u cosine theta. If we are at same point, then theta is this angle. I intentionally rewrite it now in the simplest form, divided by r squared. It's it's a dipole flow. So potential decays like 1 over r squared. It's electrostatics all over again. So velocity would decay as 1 over r cubed as an electric field of this flow. And we derived the force acting on this body. And we found, to much of our surprise, that this force is a time derivative of, let me write it, 2 pa rho water outside over 3 minus ddt of r cube u. Okay? And which means that the force directly come out of differentiating over time this factor. It's essentially written in the reference frame moving with the body. So there is another time-dependent factor here, but then you can check that it does not contribute. That was a sphere, the simplest case. This is the first lesson which fluid mechanics taught the rest of physics, and this lesson is called renormalization. It tells you that if you apply any force to a body, of course, it's equal to time derivative of the momentum of this body. For air bubble, this momentum is negligible. For water droplet in an air, just the opposite, plus some extra derivative of something which is related to the medium in which you move. So if, for example, there is vacuum here, there is no, or air, which is negligible mass, there is no momentum of it, still, by moving in a medium, you acquire inertia, right? Higgs mechanism is already here. As we now know, all masses are of this origin. It's because something moves in a medium. It could be Higgs medium, that it will be just all the masses. So this is a very important lesson going back to 19th century. And it's the first example in physics of renormalization. So you have mass. If you move in a vacuum, that's your mass. You actually move in a Higgs field, right? But if you move in extra medium, for example, in water, then you add extra mass, okay? This simple formula already teaches this important lesson. But it will teach more. At the end of the lecture, you will see that it will also teach us anomaly, which is another great theme in physics of 20th and 21st century. at the previous lecture, Olivia asked what happened if we move a body of arbitrary shape. Would that be true that still our force would be only due to changes? Okay? So if we move kind of an arbitrary body with a velocity u, how the hell we can actually compute the force acting on a body? Because for this we need a pressure field on a surface and integrate it. I won't do derivation, and I spare you this 20 minutes derivation. You can find it in the book. But as I said, it's because of a potential theory. We have a potential flow, and the general lessons of potential flows, at least that what I remember from my student days, that you can say something about here by looking somewhere there and doing integration, and then because everything is a gradient, so some integrals would be related to these two things. So essentially, the idea is that you consider very far from your body, and you ask, what is the potential over here, very far from it? Of course, very far from a body, the potential is the first surviving multipole, right? Which slowest decays. As we discussed, in Laplace equation in 3D, the solution of Laplace equation is 1 over r in all its derivative. 1 over r is a charge potential, grad of 1 over r is a dipole, 2, 2, 2, 2, 2. What do we expect far from the body of arbitrary shape? I'll give you time to wake up out of morning stupor. So the question is simple. Why is it 1 over r, or the next guy dipole, or the next guy quadrupole? Again, I ask you to answer, at least within yourself, immediately, and then start thinking. What you, huh? Dipole. Dipole. So when we look far away, we don't see the shape of this body, right? We just see that it moves with the velocity u, that's all we see. On the other hand, you can argue that 1 over r, a charge, could not enter, because then you can compute the flux through this, like Gauss' theorem in electrostatics, and it's non-zero. But it's incompressible fluid. It cannot, enter the sphere or exit the sphere. So of course, this phi is a gradient of 1 over r. But it's a scalar, and it's a vector. So there must be another vector over here, and it must be somehow related to this vector. In this particular case, it was just proportional to this vector. This is u grad 1 over r with some factor. But for a body of an arbitrary shape, it could be a complicated relation, right? You could be like this and moving sideways, and then your kind of potential over there would see some. So what we can say is that this ai and uk are related by some tensor which is shape dependent. Right? That's the most general condition. Why I used linear relation here? Why linear? Because I can make vector out of a vector in a myriad ways. But I use linear relation. Why?
Far away.
Because I'm far away, I'm using lowest multipole. But linearity has nothing to do where I am. My velocity always linearly related to the velocity of the body. Huh? No. No, it's arbitrary shape now. It's just an octopus moving.
Boundary conditions?
Yes. Because I'm solving linear equation, and my boundary condition is linear in U. Okay? So you solve linear equation with a linear boundary condition. Everything in your solution is linear in this boundary condition. Yes, that's very good remark. Yes, Peter?
We know the body won't rotate. It's a floating bubble. We know that it won't rotate.
Oh, well, at this moment, I assume that it moves without changing its shape. But in a moment, you'll see that it would enter in the force. So if you would changing shape, you're still in my remark from after 5 minutes, okay? So now, in this particular case, you again may show that your Fi is ddt of MIK UK, and MIK could be expressed through this alpha, whereas this expression is 4 pi rho alpha IK minus rho V naught delta IK. In this particular case of a sphere, the MIK is rho, let me put it up so that you can. I apologize to people on the flank. I'll move left, and at the end of the lecture, they will suffer, and you will see all the formulas up close. So for a sphere, it's a rho V naught, it's a volume of the body, whatever, delta IK over 2. It's called induced mass, added mass. This is mass renormalization in its full glory. And now, look at this formula, particularly on this manifestation. Now, Peter, to your point, what if I'm changing shape? You're swimming breaststroke, okay? So you're doing this one, right? So here is your area is small, here is your area is large. What happens when you do this? You sharply, if you're a good swimmer, reduce R. What you will get out of this formula, U is constant in this moment yet. ddt of R is negative. Your force is positive. What does it mean? As every good swimmer knows, pushed forward. Octopus is very, very effective in this. I really want you to think about it for a moment, because when I realized it, I was truly surprised. So you have a body moving with a constant speed. Whatever propellant has it does not matter. It shrinks and it accelerates because of a pressure forces by fluid acting on it. Okay? That's what it tells you. That's how added mass works. That's how you expand, you decelerate. That's why when we're doing breaststroke, we really want the glide phase to be short and fast. And then we slowly move it this, because it's ddt which comes here, right? In a viscous fluid, all the bacteria, they swim by a different law. Okay? Now, as I promised you, to show that what is this is not a momentum of the fluid, as we discussed yesterday. Okay? It's a quasi-momentum of the fluid, and now I'm going to derive it as I promised last time, because I think it's a good way for people from other parts of, yeah, this is it. Yeah, good. To appreciate connection between solid state, liquid state, and whatever.
Can I ask, before you move on, can I ask
Yeah.
about the simpler case?
Yeah.
The original sphere? Because it's also, I don't quite understand. So this formula, that's the force. What's the mass? You know, F equals ma. So it looks like already ma, but it's really a force that you set equal to a mass.
That's the mass. So what it tells you that for a spherical body, you move as if your added mass, whatever mass of the body itself, let's say you are moving an air bubble, it has zero mass, very small. But now you need to apply force to accelerate, which is a time derivative of this mu. This is your mass that you need to accelerate. This is your added mass. It's sometimes called induced mass. And for a sphere, it's half of a displaced fluid. For a disk, it's much, much larger than half. For a needle, it's much, much smaller than half. It's shape dependent.
Sorry, I'm confused again. So you have a formula, F equals to some dot.
F equal to ddt.
Okay, what is F? Or what?
It's a force.
Is that F equals ma, or is that definition of the force, or
Yeah.
expression for the force?
What we computed,
Expression for the force.
it's a force acting on a body from a surrounding fluid. It's an integral of pressure over the surface of my body.
So that means I set this equal to some ma to get the acceleration.
Yes.
Which is also u dot times some mass. What is that mass?
For sphere, it is this mass.
But what density of the?
Oh, it's density of the water surrounding
so
you.
that's what's confusing.
Why?
That's why those guys cancel out. You get u dot equals.
You have a air bubble, has zero mass, okay? Now you see that you applied some force, and you see that it provides some acceleration. As we know, for air bubble, if you apply Archimedes force, it would provide acceleration 2g, not g. So you ask, where the hell this 2 comes from, okay? And the answer is that your Archimedes force is the weight of a displaced fluid. But the mass that you turn into motion in a fluid, it's half of it. That's why your acceleration is 2g. Okay? That's this, but it comes out of computing flow around the body, calculating pressure on a surface, integrating this pressure over surface. That's where this force comes from.
So
It's your resistance force.
It's just, I understand the physics, it's just, it's not, it doesn't correspond to setting equal to the mass of the object that's moving. Because otherwise it would be zero and you would get infinite.
It's our way to get used to it. There is no object moving. There is a complicated velocity field producing pressure on the surface of the body, and the resulting this pressure gives you resistance force, which is equal to this one. So if you want to keep your body to have acceleration, you need to apply exactly that force, because that's a force applied by a fluid on you. We interpret it as if we are moving a mass. We call it induced mass. And it's effectively half of the mass of the displaced liquid. Okay? It's the density of the liquid times volume of the body by 2 for a sphere, and there is some other factors for some other shapes. That understood? More questions about it? Huh? Like you're saying, okay, here is my electron, it moves in a medium, it has some effective mass because it disturbs the medium, and the disturbed medium applies some forces on it. It's the same. It's just the first example. And everything else was flowing from here, including Higgs. Yes, Julie?
This might be a bad time to ask this, but I mean, I'm used to bubbles being low Reynolds number and very quickly coming to a terminal velocity. So this must be quite a big bubble, or...
Reynolds number will appear in half an hour, and so we now assume that nobody knows. Well, there are some overeducated people like like us, but at this moment there is no Reynolds number. We're in ideal fluid.
Yeah.
We're really at the beginning of 19th century, which is a very exciting time in fluid mechanics. But effectively, bubbles which are more than a few millimeters already go by this law. Few millimeters and less, it's a totally different story. It's a Reynolds number, it's a viscous flow. The resistance force is linear in velocity and times viscosity, all this stuff, okay? So this is a big bubble. Yes?
Adding a little bit to that, would that then appear in the force equation with the fluid applying, the fluid?
Fluid applies different forces. And I won't do it, you can just look in the book. You can compute, when we'll introduce viscosity in half an hour, then you understand that apart from pressure, there is also tangential forces, friction forces acting on the surface. They add to it. Miraculously, for liquid, they are just the same. I mean, you have a tangential force and you have a normal force, and for a sphere in a constant motion, they are the same. Okay, but it does not matter. So far, no tangential forces, no friction. Okay, good. More questions? Good. So now, what I want to show you that this ddt, what it stands here, as we already know that it's not a momentum, because if we're in the enclosed volume of a liquid with a constant wall, there is momentum of a liquid is 0. But it's ddt of something which is mass times velocity, right? So it's, and what I'm now want to show you briefly is that it is called quasi-momentum. And so QM is not quantum mechanics, believe it or not, it's quasi-momentum. And I want to briefly remind you what it is and derive it for a fluid. Essentially, the easiest way to define it is to say that you have a Hamiltonian system. Hamiltonian system is such a description in which you have an even number of variables. So you have some momenta, a set of, let's say, pj, and you have some coordinates qj. But what we assume on top of it, that both your momentum and your coordinate depend on some extra variable x and of time. They also depend of x and of time. And of course, we know what is the equation of motion. P dot is dh over dq with the respective index. Q dot is dh over dp. One with a minus, another with a plus. Now what we want to do, we want to say that our Hamiltonian, even though these guys dependent on x, x will be our coordinate inside the medium. So we have liquid, or it could be a crystal, then x will be discrete because you are on a lattice, right? But we want our Hamiltonian to be independent on x. Now the derivative of Hamiltonian, and I assume that x is a vector because it's a coordinate inside. It's a vector coordinate inside my media. So I want the x, the h, dx to be 0. And it's, of course, dh, d pi j, d pi j over dxi. And over j will be summation like Einstein convention, all repeating indexes. I will be summing. There will be dh over dqj, dqj over dxi. And I want it to be 0. I'm saying, OK, it's a symmetry, right? It's a symmetry. It tells you that you shift by x and your Hamiltonian does not change. So I now want to find a conserved quantity which is conserved. So this would be 0 just by virtue of z. But k, of course, is some function of pi and q. And time derivative of any function of pi and q is a Poisson bracket with a Hamiltonian, right? So what I need to do is I need to do dk d pi j. Incidentally, that will be a vector, ki over pi j. And here will be d pi dt, but I know what is d pi dt. It's dh dq. Right? Now plus dk dqj, and here dq dt, which again I know what it is. It's dh d pi. Right? Now I want this to be this and that to be that. In this case, I will have a conservation of this guy by virtue of invariance of a Hamiltonian. Well, you've seen it many times in different. I'm just trying to kind of put it in the simplest form. So essentially, you need to solve two equations. dk d pi is equal to dh. Huh? Huh?
Like the dh dq on the left, on the bottom left, should be correspond to the top right.
dh, yeah, absolutely right. So this is, must be like this, and this must be like that. So I need dh dq, dh dq. So this guy would be equal to this, right? So I would have my dk d pi ji equal to, sorry. So this guy would be equal to that guy, right? dq j over dxi. This is my derivative. I'm solving two partial differential equations. K depends on pi and q. That's a derivative of k with respect to pi. dk derivative over q, ki qj. This one comes out of here, and it's minus d pi over dx ij. Okay, good.
Sorry, what is the minus sign?
A minus sign is because here dk d pi dt is minus dh dq. Sorry. Okay, good. That's mine? Okay. Let's say if I ignore, maybe it will forget about me. So the solution of these two equations is pretty simple. Again, it's a vector. And it's an minus integral over dx of pj dqj over dxi. Just by looking at it, you can easily convince yourself that if you differentiate it with respect to pi, you get dq again at a given x, right? Everything is at a given point x. If you differentiate with respect to q, you integrate by parts, and you get plus, okay? Now what is left is to ask what is the Hamiltonian momentum and coordinate for a fluid, for an ideal fluid. And, yes? The sign, yeah, over Q must be minus. So I guess, no. Now it's right. Okay, good. Catch my errors. So now, there are many ways to write equations of ideal fluid in a Hamiltonian form. But for this reason, the best way and the kind of easiest is to write it in a Lagrangian particle form. Again, you remember that we can write everything as a field theory or as a dynamics of particles. Now, because we have an infinite dimensional medium with infinite particles, it's really kind of two equivalent ways of doing things. So what are our Q and Pi's? So remember, I remind you, what is Lagrangian motion? I assume that coordinate of a particle depends on its initial coordinate and time. So that r of x0 is x. That's my definition of a Lagrangian coordinate, and x is its initial position, or sometimes we call it marker. Okay, so you can kind of imagine that every fluid particle has a number of it. We just numbered them. And in this, I won't go into it, I just mentioned you that Kelvin's theorem, conservation of vorticity in the respective form, is a result of a relabeling symmetry. We can relabel our Lagrangian marker. It's a very beautiful mathematics behind it. I won't go into it. So now I introduce Q and P. And it's again, for solid state people, it will be immediately recognizable. I introduce Qi as Ri minus Xi. Okay? It's just a displacement. Right? So I was in X, now I am in R. Like, it's a function of time, it's a function of time. This is its initial position, okay? When you do phonons in solid, that's what you use, a displacement of any particle, which in this case is number. And of course, my pi would be a momentum, and it will be something which would be rho naught. I assume that at the beginning of time, I had all my particles distribute with some rho naught. It's usually take uniform. You can play beautiful mathematical games relabeling your initial position with a non-uniform density. I won't go into it. It's just a constant. You can put it unity. And of course, times velocity. And velocity, everything is now a function of x and t, right? There is no space here. Only number of particles, which is x, a label, and time. Okay, so velocity depends, again, is a vector of x and t. And of course, velocity, it's a derivative of coordinate at a fixed x, which is what we call Lagrangian derivative. So it's a derivative which keeps the particle, right? Which in this case means a finite x.
The x, or the x is the coordinate in space?
X is a coordinate of space of a particle at the beginning of time, at the Big Bang, or whatever you start. It's a Lagrangian coordinate, which is initial position of your particle. Or you may call it a label. R is a position of your particle. So this is a particle description. You follow particle, this is R where it is. This is X where it was. So it's labeled by its initial position. Whatever time derivative you take under constant X because it's for the same particle, right? Okay? So when you write this, it means that. That's Lagrangian description. It's very, very powerful. You know, as a friend of mine once joked, not a little risky joke, say some things are better doing than watching, right? And this is Lagrangian way is a way of doing fluid mechanics, right? So you go with the flow, okay? And this is a description. So now, because we have coordinate and momentum, and we know the equations, by the way, right? So we know that dr dt is v, but it must be a dq dt right? Must be the derivative of Hamiltonian with respect to pi, right? We know it. And I also know that d pi dt must be minus derivative of Hamiltonian with respect to q, which in this case with respect to r, and this is j, and this is j. But of course, it is just time derivative. So this must be Euler equation. It must be something which is dv dt is minus ddr vi enthalpy. Let's say we consider isentropic flow for simplicity. So it immediately tells you that your Hamiltonian, of course, it's again, it's an integral over dx. It's got this rho naught. You have v squared over 2, which is your kinetic energy. This is effectively pi squared over 2 rho naught. This term, right? This is kinetic energy.
W is
It's E plus P over rho. For incompressible fluid, it will be just P over rho because.
very quickly.
Sorry. It's Euler equation. Minus grad P over rho. This is minus grad P over rho. And for enthalpy case, it's just, okay. And of course, this would be plus W. So that's my Hamiltonian. And it's surprisingly powerful way of describing fluid mechanics and not very often used because, again, this Lagrangian. Now, of course, for this case, it's pretty easy now to, and then you see that dh d pi would give you just v, and dh dq just will give you Euler equation. Now, what is a momentum? Quasi-momentum. Where is my quasi-momentum? Is up there, okay? So now, you don't express pressure. This now pressure is your Hamiltonian. As I said, I mean, this is for incompressible fluid. So pressure, this is what makes it so, because I mean, like for 20 years, I'm trying to use it to do statistical description of a fluid motion because I now have Hamiltonian, right? So I can do all the Gibbs stuff. But it's a Hamiltonian which depends on coordinates of all my particles. So you have particles which interact through this potential, and this potential depends on positions of all particles. That's what pressure is. Pressure describes interaction between particles. So you want to look at it as if it's Coulomb gas or whatever. That's your potential of interaction, and it depends on time because all the positions of particle depends on time. So it's not very. It's probably somebody with better mathematical skills someday will use it for a very beautiful way of describing fluid. But for now, I'm using it for deriving quasi-momentum because it is now straightforward, right? And it tells you what's the difference between quasi-momentum and the whole momentum. Let's see.
V squared over 2 just comes from the first equation.
Huh?
V squared over 2 just comes from the first, to get the first equation.
Yeah, yeah. Because the first equation, you differentiate it, you get 2 pi over 2 rho, which is V.
This is under assumption of constant density.
At the beginning. Okay? Incidentally, if you're interested in what is the present density, which is a function of coordinates, then of course you have a conservation of mass. So your present density is your old density, which is unity, times Jacobian of transformation from x to r, right? Good. So now let's write what is quasi-momentum. And quasi-momentum now is minus rho naught we can take out, integral over dx. And as it must be, pi dq dx, here is our q. It would get here v, and this is ki, vj, dqj over dxi. And now if I take that my q is r minus, then I would get delta ij. It comes out of differentiating xi with respect to xj, and minus dri over drj over dxi, and then I would to a plus. It's a simple but very important formula. Let's meditate a little bit. So if there would be no such term, right, what that would be? Integral of v dr, right? Dx, dr, dx, this is just v dr, it's a momentum. No, we say, it's actually difference. What is the difference? What I subtract? When I go far away from a moving body, for example, when there is almost no disturbance, then this turns into delta ij, right? It almost don't disturb, and it's all cancelled. It cancels this infinitesimal counterflow which is far away. You see this difference. So when you did phonons for solid state, when you look at the displacement, you were using Lagrangian coordinate. And by the way, again, look into the book of Pyrrell, Surprise in Theoretical Physics. It explains what it means that phonon has zero momentum and what it means that moving fluid has a non-zero momentum. It all comes down to this Lagrangian picture. I won't go into it. You can also find in my book. So this is a quasi-momentum, and it's described by this formula. And the last thing which is remaining is to prove that this guy over there, it's the derivative of that guy over here. Okay? So what now I need to do is to compute dk dt and prove that this is this. Okay, and that would close the circle. I do it kind of briefly.
What do you mean it's this? It's supposed to be conserved?
It's conserved if I do not apply extra forces. If I apply extra forces, namely I move a body through a fluid, what I now want to consider that in my fluid, I have a body, and I have some pressure field outside and velocity field outside, etc. And I want to compute a derivative of quasi-momentum of the fluid and prove that it's equal to the forces acting on the body. Okay? And of course, it's done like this. When you differentiate this guy, what you need to do, you need to differentiate this with respect to time. So it will be rho naught integral dx dv dt delta minus dr dx, plus you would need to differentiate this, right? Which would be rho naught dx v, but this time derivative of r is v, right? So what I would have here is dv dx. And it's zero, it's a total derivative, right? Because I integrate over dx, dx of v squared over 2, right? So now, when I get rid of this term, what I need to do, I need to substitute here dv dt, which is by Euler equation, is a gradient of pressure over rho. Then use this, let me write it with a little bit more detail. So I would get it as a result as an integral, and rho naught dx, I, by this transformation, would replace by rho dr. So now I am integrating not over initial position, but over real coordinate at that moment of time. And that would be here, which comes out of, it will be grad pi over rho, that what comes out of dv dt, right? With a sign minus. Now, rho cancel out, and that would give me an integral of pressure, of gradient of pressure over volume, which is everywhere disappears except this guy. And the integral of pressure over this could be turned into integral of pressure of a surface. that's a proof that the integral of pressure of the surface of a body, it's a time derivative of quasi-momentum. And it explains you why by shrinking you actually apply force to it. It's a liquid which applies this force to you because you are changing flow. When you're changing your shape, you're changing flow, you change pressure distribution, and it applies forces. Yes?
I guess you started back there by saying that the Hamiltonian has this, that the HPX is 0. I'm just trying to, you've written Hamiltonian up there.
Yeah, I assume that dH.
How do I verify that the HPX is 0?
Oh, no, you don't verify. You assume that your Hamiltonian does not depend on in which part of fluid you are. X is a coordinate of a fluid particle. You assume identity of all fluid particles. That's the symmetry that you're exploiting here. And it's a different symmetry from a homogeneity of space which gives you momentum conservation. Is that understood? The moment you have a medium, then translation invariance has two phases, right? One just translating in space, another is by looking in different elements of a medium and saying that they are the same. In a crystal, your translation in space is continuous, but your translation in medium is discrete. That's why your quasi-momentum in a crystal lattice is a discrete thing, right? More questions? Yes?
What's the relationship between quasi-momentum and pseudo-momentum, like geophysicists discuss?
The relation is, the question is, what is the relation between quasi-momentum that I introduced here and pseudo-momentum that people use in a geophysical fluid mechanics, essentially? They are the same, but it takes a lot of effort to see it, at least for me personally, okay? But if I'll give you the simplest answer, they are the same. But because this quantity has many manifestations, when you start thinking about waves, it's also potential flows, and then you can relate this to a potential. This is nothing about potential flow here, right? But for potential flow, it's very simple because, and I won't go into it. So it takes effort, but essentially the same. More questions? Yes?
You're doing your work in canonical coordinates. I've seen a lot of Hamiltonian fluid dynamics using non-canonical Hamiltonians. Do you have any comments about the distinctions?
The question was that I'm doing it in a simple canonical coordinates like particle mechanics. But there are different formulations of Hamiltonian formulation of fluid mechanics on a field theoretical language. Namely, when you use symplectic form, right? Because, I mean, you have earlier equation, and it's nonlinear. It's dv dt v grad, so it has a quadratic form, right? But you need kind of symplectic structure, which means that there must be a variation of some Hamiltonian. I won't go there. It's a complicated and beautiful mathematical field. It used in physics very sparingly. I mean, not much, unfortunately. But there are some beautiful algebraic structures behind it, which I think will find someday its place in real practical things like turbulence theory. And tried it when I was younger and more brave, and I failed. So yeah, okay. More questions? Leo.
Just ask, so I want to try to relate it to that formula. So let's say I have an example where you started with champagne and there's gravitational force.
Yeah.
So that P is going to turn into mg?
Yeah. What is this? It's precisely what we derived there. We've got this formula exactly solving equation, finding pressure everywhere, taking it on the surface on the sphere, integrating it over sphere.
That guy is, okay.
So that guy is that guy.
Okay.
That's it.
But then where's the, well, so let's say in the case of you just have gravitational force and that's acting.
The gravitational force would be equal to this time derivative, namely that if you look at your, so the question was how it's related to the example with the bubble. So for the bubble, you have Archimedes force, which is a mass of a displaced fluid times gravity acceleration, and it must be equal to time derivative of the quasi-momentum, which, as we know, is half of a displaced fluid. And that's what gives you 2g for a bubble. Okay? More questions? Yes?
When does that assumption fail? The thing that everywhere it's the same when you're taking the derivative of xi? You said it's
Well, this assumption fails in like Well, the question was where this assumption fails. You mean this assumption is that the force is this time derivative?
Oh, no, the derivative Hamiltonian with the position, like saying that.
Ah, you mean that assumption that actually, where is my, yeah, so, right. So the question was where this assumption falls.
No, when does it fail? Like,
When this assumption fails, so when the assumption that my Hamiltonian, it fails when my medium is inhomogeneous. For example, if you take a crystal and try to shift by half lattice space, it won't be true. You won't be in the same atom. If you have an impurity in a crystal, it fails. Okay? But you essentially assume that your fluid particle, it could be different density of your fluid particle. You can consider compressible flow this way. But you say, this is the same fluid particles. Imagine that you're trying to describe this way a cloud. Cloud has air, is one fluid, and water droplets is another fluid. If water vapor is yet another fluid, then it would be true. You need to, well, it could be done, but with with some generalization.
so if you're thinking of like, if there are two, you wouldn't be able to do this whole thing if there are like, if you want to describe.
This symmetry is homogeneity of the medium. It tells you that all your fluid particles are the same. That's all what it tells. Or it tells you that all your atoms in the crystals are the same. The moment you have different atoms in a crystal, you would need to use different shifts to get into the same atom, right?
So conventional momentum is still conserved, where you move the whole thing.
Conventional momentum, the question was a conventional momentum. Conventional momentum is, of course, still conserved because your space is still homogeneous.
One is motion in reference space and one is in target space.
But for example, if you're interested in solid-state physics, the conventional method just tells you that you can move your crystal as a whole and it's okay. It's okay, so you can move it in the next room. But now it's much more non-trivial. You can move inside the crystal from this part of a lattice to another part. That's what makes quasi-momentum. That's what something is about phonons, because that disturbance of it. That's different symmetry. Okay? Yes?
Related to that comment, so if I look at the equation that you wrote for quasi-momentum, just the first term, ignore the drdx, that looks like regular momentum to me.
Yeah,
right? So
absolutely.
if it's conserved, then why can't I just...
It's a momentum minus reflux.
Right.
Which means that because reflux in a big medium is distributed everywhere, that's what makes quasi-momentum very local. It's local. You subtract, you see this delta ij, when you subtract this, you make this integral, first of all, it make it converge. Because if you look at this flow, it's another, thank Aaron, this is a very good remark. If you look at this flow, just look into it. Phi is 1 over r squared. Velocity is 1 over r cubed. Try to integrate it in three-dimensional space. You get diverging integral. This integral converges. That tells you that quasi-momentum is localized near the body. And And the last beautiful piece, again, I won't derive it. I just want to show you what a kind of a beautiful physics is behind it. So what is the relation to the displaced mass? And what actually way you displace the mass? So let me ask you the following question. Here I have my sphere. For the change, because now I'm on the right, I'll move it to the right. So this was at the beginning of time, it was here. At the end of time, it is there. I look here at a fluid. Let's say I take fluid particle which was here at the very early time when my sphere was far away to the left. Where this particle will be when my sphere will pass it by? To the right or to the left? Answer immediately. Left, right? Left. Because I vacated some place here, right? So there was no fluid here. I moved it here. My fluid must move to the left. Somebody thinks it's wrong? My hypnotic abilities aren't that great as they used to be. Again, does it seem reasonable that when I move something from left to right, my fluid, on average, it would move complicated way, it would move sideways, right? Because I'm pushing it. Definitely in front of me, I'm pushing it this way. But from behind, I'm pulling it, right? To feel it. What will be the net? Look here. You want to accelerate bubble in this direction. Which way would fluid apply to you? This way or kick you from behind if you try to accelerate forward? So I'll give you the answer, and you meditate about it. The trajectory of every particle, yeah, let me, okay, maybe I just, it would be here. Initially, I'm pushed, as I'm moving from here. I push it this way, I push it this way, I push it this way. Then, if you differentiate potential, and you will see velocity, which is electric field, you will see 3 cosine squared minus 1. It tells you that when you cosine square is 1 over space dimensionality, your velocity changes sign. It ends up here, initial, final. Now, if you look at a particle which is further away, I want another color, yep. Of course, it would start, let's say, somewhere here and move like that. If you just sum all these particles, all particles which were here would be symmetrically shifted right. And this is, if you integrate it, which were done by Darwin, but not Charles, but well, also Charles, but his grandson in 1953, it's half of a displaced mass. It's an induced mass. So this is your quasi-momentum. It's the shift of this. Every fluid particle goes right, left, right. But net result, of course, right. Because that's where you push your fluid. That's why it acts backward on you. The momentum of this guy is what you need to accelerate when you move from here to here. Okay? Yes?
What happens if the particle's right at the tip of the sphere?
What do you mean? Over here?
No, so it's moving like this, and then there's
You mean?
right here.
Well, I'm talking about particles which were initially far away from a sphere, right? The particle which is here just shifted. I mean, it's ideal fluid. There are no tangential stresses. The fluid always flow kind of past the sphere. There's no problem with it.
But the boundary conditions of
The boundary condition only about normal velocity. Tangential velocity of a fluid on a sphere is non-zero if you look at the solution. Just look, by the way. This is a good thing. What are the tangential velocity on a sphere when my potential of velocity described by this formula? Compute it and find out that it's not zero. Okay? Good. Aaron?
So what about behind the sphere? So the way you've drawn it is the particles in
Yeah.
front,
So,
behind this is the same thing.
yeah. Well, the question was, what happens to the particle behind the sphere? So essentially, what I need to do, I need to kind of make all this. This is kind of a long surface, right? So there is something over here which would definitely move this way, right? But it would give you very small contribution. This integral is mainly this integral. Look at this Darwin paper, by the way. It's readable. Everything which Darwin wrote, it's eminently readable, and it's a very beautiful computation. And it also shows you why quasi-momentum indeed is related to the motion of a fluid particle and how non-trivial this motion is. Yes?
So what if the particles at the middle of this part?
The question was, what is to the particle to the middle of this particle?
That trajectory seems like decay.
Yeah, well, first of all, the question was what happens to this particle, what happened to that particle, what happened to that particle. Do it yourself. Take this formula. It's, for God's sake, dipole field. You are supposed to be, like close your eyes and immediately write electric field for the dipole potential. That would be your velocity field. Take x, y coordinate and look at different points what it is, okay? Relatively to the position of a sphere. Okay, good. I'm stopping here because I want to show you anomaly. I want to show you the next lesson, which we draw from here, right? So now we have half an hour left. And we are now trying, I want to switch gear and ask the question which kind of looms all over this thing. What if everything is constant? What if u is constant and radius of my bubble is constant? What this formula tells me that the force is zero. that if you take whatever body it is and move it with a constant shape and constant velocity through an ideal fluid, the force is 0. It's better than free lunch, right? It's just. On the other hand, if any force in any direction, right? For resistance, it's immediately idiotic because we all know from experience that we encounter resistance. And but birds and airplanes would immediately fall because they move with a constant speed, but they have lift force, which lifts them, right? If that would be true, that would be 0 because the force is ddt of quasi-momentum, and quasi-momentum is constant. So what saves the day? What Feynman calls it the theory of dry water flows. That's what we did so far. Let's go to the wet water. And what's the main difference of a real fluid and the ideal fluid? Viscosity, friction, yes, it's friction. So we now need to account for the fact that, of course, when we move through fluid, we would have a tangential forces. So first of all, I want us to guess what would be the true resistance force when we take a body of a radius r, moving with the velocity u, and what would be the force acting on a body? Just let's guess it, like normal people with a normal physical intuition. And then we get introduced viscosity, all that stuff. So I move it with the velocity u. I push fluid in front of me, right? So I give it momentum, which is momentum that I give it would be r squared times u, right? And then it would be with a rate which is proportional to u itself. And it would be, of course, density because, so I'm having rho u times r squared u. Some coefficient which is shape dependent. You can say that this is like effective pressure, which is rho u squared times area, which is r squared. Newton wrote it in optics, which is, I mean, it was kind of well hidden from. That's the only estimate that you can get, right? It also happened to be true. How to derive it? And that's the clear example that if you have no friction inside, this is the answer. Now, this is a true answer, which has no friction in it. There is no viscosity here. That's the first example of anomaly in physics. Let me tell you what is anomaly. Anomaly is it's a modern jargon to an extent, that you take something which breaks a symmetry. Friction, tangential forces, breaks very important symmetry, which is time reversal. Okay? We need to break time reversal symmetry to have resistance force, because resistance force must change sign when you change time direction, when you change u to minus u. And yet it's quadratic in u. Just the very fact that you have resistance, this is a true formula. You can just go and measure it, right? The very fact that you have resistance proportional to u squared, even though it's something which is odd in u, tells you that you have something inside your fluid which definitely breaks time reversibility. You consider limit of very large bodies, a very large Reynolds number. In a moment, Reynolds number would appear. In a sense, you may say that your viscosity, what breaks the symmetry, goes to 0. So the symmetry breaking factor goes to 0, and effect of symmetry breaking stays finite. Okay? That's what this formula tells us all the way since 18th century. It took a lot of time to understand what actually this obscure remark of Newton in optics means for us. and dissipative anomaly in turbulence just follows from here as well. Okay, so now how to get it? It's a painful road. We'll introduce viscosity. We'll consider what it does to the flow. Then we'll turn viscosity into 0, and we'll see what happens when we turn viscosity into 0. This is a very long road, not completely followed. We have 25 minutes for it. Let's do it, okay? Questions at this point? Yes?
The stuff that you wrote in red, was that from dimensional analysis?
Yes. What I did from dimensional analysis and common sense. I say that, the pressure is rho u squared by estimate, right? This kind of pressure difference, if I push it here, so the pressure here must be larger than over here. And so if I take pressure and times area, which is r squared, it must be force. So it's common sense and dimensional analysis. You can do anything else out of rho, u, and r, okay? Good. Viscosity.
I mean, if you put that, because it's even in U, it's not going to reverse. This friction is not going to reverse.
That's anomaly. The answer is, technically looking, is reversible, but real resistance force is irreversible. So what stands here is like a sign of U, which is very non-analytic. Okay?
So it's really sign of U.
It's a really sign of U there, right? But, dimensional analysis cannot give you sign of U.
Common sense.
And common sense means that it's like 200 years of fluid mechanics. Yes?
I want to make a comment about the particle relabeling symmetry. As Jeff mentioned in the Deadlist lecture, there are a lot of different fluid equations, particularly in GFD, and each of them have a conserved quantity that's different. And they're connected because they all come from particle relabeling symmetry, and it's manifested in different equations in different ways. Previously, I had thought that all of these conserved quantities had been discovered before the realization that they come from particle relabeling symmetry. But there's a brand new symmetry, a brand new conserved quantity that just, the paper came out in June for moist geophysical flows with phase transitions, water vapor, condensing, and evaporating.
I'm not sure I would be able to repeat this remark. So maybe yeah. So maybe you would better make it on record using the mic, because we're.
And so there's a recent work where they used particle relabeling symmetry to discover a new conserved potential vorticity for moist flows with phase transitions. So that's a really interesting application.
Okay, I think that if you put it reference in Slack, then we can all read it. Okay, so now what I really want to do to introduce tangential forces. What does it mean? You remember that we wrote the equation for a time derivative of momentum, and it was minus space derivative of a flux of momentum, which was the just transport flux of a fluid, the pressure delta IK, this was K, right? And now we need to add to it something else, would be the fact that when we move this way, there is also transport of momentum this way because of tangential stresses, right? So let's call it minus sigma IK, and it's a called viscous stress tensor, which comes out of tangential forces. So if I have x and z axis, then this would be sigma xz, right? Xz. It's a force acting in x direction on a plane which is transversal to the z direction. That's a definition of sigma ik. The force or momentum flux, if you wish, in this direction through the area which is normal in k direction. So respectively, this would be sigma zx. Now, are they equal to each other? Or in other words, is this a symmetric tensor? Answer immediately, yes or no? Good. So we answered immediately yes, and then we ask why. So why it is a symmetric tensor? Well, the simplest way to see it is to say that let's look at this element over here. And of course, it's three-dimensional, so it has this thing. So if I would say, consider its action with respect to this action, okay? What I need to do, if I want to understand whether it would rotate this way, namely this means, or that way, namely that means, I need to take sigma xz minus sigma zx and multiply it by delta x, delta y, delta z. So sigma xz multiplied by this area and this distance would give me a momentum of the force acting on this plane with respect to this. In the same way, sigma zx, I need to take this, multiply by this element, and times this momentum. And all this must be mass, which is involved, delta x, delta y. I remember, Julius, that I need to write more clearly at the end, so I'm trying now to do a little bit more calligraphic. This is my mass. What must be here? It's an inertial tensor, namely, it's this distance, delta x squared plus delta z squared at times d omega dt. That's an, again, earlier equation. The same Euler derives the equation for the rotation of a body. Incidentally, as Arnold shown, these are the same equations, which is a finite dimensional version of it. Now you see that when delta x goes to 0, shrinks. This is delta x cubic, and this is delta x fifth power. So d omega dt would be infinite for infinitesimal elements. And that's what requires this to be 0 and our tensor to be symmetric. Now, what is really difficult, and what Newton first faced, is how to relate this tensor to the velocities. Because somehow it is the inhomogeneity of the velocity flow, the dependence on velocity of coordinates, which causes the tangential stresses. And Newton assumed that there are liquids, fluids, gases, for which there is a linear proportionality between sigma ik and dvi over dxk. Well, let me get ik lm. Now, if you want to connect two tensors of a second rank, what you need here is a tensor of a fourth rank. All my life, I never handled such tensors, except a short period when I was plasma physicist, and I hated every second of it. And it would make a fluid mechanics really complicated matter, and some people in plasma physics do handle even asymmetric things. But what is fortunate, and what already Newton recognized, is that out of this tensor, only symmetric part enters, because the antisymmetric part of it is what we discussed yesterday called vorticity. Vorticity is a rotation of a fluid element as a whole. Solid body rotation does not create tangential stresses, right? Because a fluid layers move together, they don't move with respect to each other, okay? It makes it extremely easy and beautiful that what comes here, it's really and if you assume that it's an isotropic medium, namely that there are two symmetric tensors in an isotropic media can be put into diagonal form by orthogonal transformation. I mean, you can always find the reference way in which they coincide. And if it's also incompressible fluid, so dV, which is dvi over dxi, sum over I is 0, then this is just a single scalar quantity called viscosity. So I really want you, while I did all this instead of immediately writing, that the moment you go out into a real world, you find media which is not necessarily isotropic, you find media which could sustain rotational acceleration, which makes your tensor. So there are many different and beautiful exceptions to this. Fluid which satisfies this are called Newtonian fluid. The moment you add sugar to your tea, you make it non-Newtonian because it's a polymer. It has a polymer molecules, and it makes property of your stress tensor very different from this relation. Right? So just to remember how much miracle is behind the single quantity. Okay? Now, questions? Huh?
That equation assumes rotational invariance.
Yes, it assumes that my media is isotropic. So the moment you go into plasma with magnetic field, forget it. Okay, and many other things. Yeah. So now, what I want to estimate it just for kind of a simple case to give you a feeling for it. So for example, if I take a gas and I have molecules flying with thermal velocities, apparently what creates tangential stress? I have fluid moving here, and some molecules can come from here to here and bring this momentum to the other places, right? So if I have a flow like this, and I'm interested in how much momentum in x direction I bring in z direction, that would be precisely tangential stress. How much of x component of momentum, which is more here than here, I'm bringing per unit time, per unit area. That would be my stress tensor. So what I need to do, I need to take the number of molecules times their velocity. That would be a flux. How much they bring. Every molecule has a mass. It brings the velocity difference between here and here. But between velocity difference between what, at what distance I need to take. Here I have a grad V, right? So this is just, which is dvx over dy. But I need to multiply it by some distance to get velocity difference. What is this distance that I need to take here? Yes, it's a mean free pass. Because I assume that a molecule would come here, hit another molecule, and will transfer the momentum to it. So what I need to take a mean free pass and multiply it by grad V, and that's my sigma. So all this is my eta, viscosity, okay? Or in other ways, you can say that this is m times n, it's rho. It's rho, thermal velocity, mean free pass. For gases, in particularly, the mean free pass is 1 over n sigma. Well, sigma is, how to call it? Well, sigma c, cross-section. So every molecule has a cross-section of scattering, and mean free pass is usually 1 over concentration times this. So if you now take eta, which is m n vt l 1 over n sigma cross-section, you would see that the viscosity of gases is independent of concentration, essentially independent of density, which is a well-known fact. And even more important, what we in a moment will see, that if you define a kinematic viscosity, which is eta divided by rho, which is m n v t l divided by m n, it's v t l. And this is a formula I want you to remember. A kinematic viscosity, it's something which is a diffusivity. Because now, when I substitute this sigma into the equation which we had, which was earlier equation, I divide by rho. You see this sigma, which is proportional. What I would get here is new Laplace V. This is a Navier-Stokes equation. It's a curious equation. It has a name of a person first who wrote it and last who wrote it. And there were like 7 people in between who did not leave their name on this equation. I don't know why, but sometimes it encourages young people to still name, do things even though some other people did it before, but maybe you'll be the last person who derived this equation and you'll get it your name. So Navier was the first who derived it and Stokes was the last, and it's called Navier-Stokes equation. So if you forget about all this, you will see that dv dt is nu Laplace v. Nu is the diffusivity of momentum. What tangential forces do, they do diffusion, right? And diffusivity is always some typical velocity times typical distance. For electrons in graphene or in whatever, this would be V Fermi. That's all, and this would be LEE. Okay, so it's a very general formula, and in particularly if I'm back to gases, what it tells you that when you heat the gas, what happens to your viscosity? It increases because your thermal velocity is increasing, right? This is something which tells you that the mechanism of diffusion of momentum in a gas is that molecules need to come somewhere. And the faster they go, the faster you diffuse. Liquids. If you heat a liquid, what we expect happen to its viscosity? Answer immediately. Increases. Decrease. You cook people. You pour oil on a pan, heat it. Have you seen what happens? Its viscosity decreases. Just opposite to what it happens to the gas. It's getting less viscous. It starts moving around. Why? Because the mechanism of a diffusion of momentum in liquids, it's totally different from the diffusion in gases. In gases, molecules physically come from point to point and bring momentum. In liquid, there is no such chance. It's already have a density more or less of a solid body. Molecules transfer momentum by forces. This molecule which moves here, it transfers momentum from here because they are pretty close and they interact. And this interaction is getting weaker when you heat the fluid, because you increase the random element relatively to your regular element which comes out of it. Okay? Good. And now I want to give you the picture very qualitatively, and we'll continue it all the way to turbulence in the last lecture, is how the hell the existence of this viscosity helps us to understand this formula. Again, here already you all know, I pretend that you never seen Reynolds number, but of course the Reynolds number is something which is relation of this term to that term, because essentially all fluid mechanics is about competition between inertia and friction, and Reynolds number is a dimensionless number. Physicists are simple people. We always think in terms of two quantities. We always ask this or this. We practically never consider three quantities. But when we consider two quantities and we compare them, they are of the same dimensionality. So what we like to do, we like to take their ratio and that make dimensionless number. Most of the physics is about dimensionless number, which means that we always consider competitions of two factors, never three. If you look at all our theories, it's either one constant theory or two constant theory. The quantum gravity does not exist so far because it would be a three constant theory, and we're just not able to handle it. Okay, so Reynolds number is a ratio of this to this, but of this to this, which is u times r divided by nu. And we would like now to go to infinity when nu disappears and ask how the hell that Newton's formula can appear. And now I'll probably use the central blackboard for the last 5-7 minutes of my talk to describe you very qualitatively the beautiful idea invented by an engineer, reported on a mathematical congress in 1905. You see how much time it took since Newton optics, which is, well, I don't remember now the date, but we just celebrated 300 years since Principia. And the idea was as following. So if you now look at the sphere, and you look at the flow behind it, and consider a very, very particle which goes very close to the center, a little bit off center. So we expect it to go like this. And this is precisely what this formula tells you. So if you just plot the velocity streamline, now we have a very, very tiny viscosity. What this tiny viscosity does, from the viewpoint of these particles, let's first of all look at how it's moves with fast velocity. Its velocity almost goes to zero here, because it's stagnation point, right? I'm very close to stagnation point. So V here is low. What means that pressure? Pressure here is high, because I have my Bernoulli theorem, V squared plus P over rho equal to constant. I'm an ideal fluid, right? So my pressure here is high, and pressure here is low, because velocity is high. I'm really this is the fastest point, yeah? I need to go around the obstacles. So imagine you're a fluid particle, right? So you're very slow here, then you accelerate, because you have a high pressure here, which pushes you from behind. And you go all the way, you accelerate. What you do from here to here, you decelerate. I was a kid, I have an older brother who also is a physicist, and there was a kind of a big pit in the earth. They say, if we run fast down, then we'll have enough inertia to run fast up on the uphill. And of course, we did it, and of course, he is 6 years older, so he did it uphill, and I was stuck in the middle of it. That's how you learn that not everything that you accelerate this way, you can then decelerate this way. So what viscosity does, even when tiny, it is a very tiny boundary layer. You can always estimate its size by this relation. You know, it's always the scale and U and nu come together. So this is the width of the boundary layer. When u goes to zero, it goes to zero. It's a very, very tiny, but there is a dissipation inside it. Inside it is a dissipation, and a fluid particle accelerates this way, and then it loses a little bit of its momentum. It diffuses away. What viscosity does? It takes its momentum, it diffuses it away, and it does not have enough to overcome. Here is P low, here is P high, right? So I have an adverse gradient. I need to move against it, and I don't have enough inertia because it diffused away. And then what it does, what this fluid particle, which is right here, and it cannot enough velocity, don't have enough velocity to overcome this pressure gradient. Which way it goes? It deviates. It goes away. Well, it being continuum motion, what appears here is a recirculating vortex. And of course, you have a symmetric picture from the other side. And this is called wake. That's how anomalies appear in physics. You have a tiny, tiny viscosity. You have a solid body, a finite body, just a finite area. Something happens on this body. You change flow forever. This goes to infinity. Prandtl, who was a guy who realized it, and of course they built a theory of boundary layers, realized that whatever finite thing won't do. You consider finite thing as a new body, and it again would have zero resistance by this formula. You need to change the flow in the infinite domain. This domain is wake, and it is precisely the deficit between this and this creates a resistance force. And the resistance force over here, this CR squared, is a wake area. The area by which you really create resistance, well, that's why we make wings very, very streamlined, so that wake is very, very tiny. But as we'll see in the next lecture, you cannot have a lift force without a wake. Okay? So the great idea and the real illustration of how even tiny viscosity, the world with a little friction, is very different from the world with no friction at all. That's the last message today, and we'll continue from this point on Thursday. Questions? You all look shell-shocked, as if you never heard the name Prandtl-Wake. Yes, please. Speak louder.
I just wanted to clarify. So when we showed that there's no resistance force in an ideal fluid, is that called D'Alembert paradox?
It's a D'Alembert. The question was: it's a statement that there is no force in an ideal fluid is a D'Alembert paradox. I hate the word paradox in physics. I mean, all my life I spent just fighting them. But it is, D'Alembert paradox was actually a very particular case. D'Alembert formulated, if you have a symmetric body, then only force which can act on it is a pure couple. Namely, you can rotate body, but there is no resistance. Indeed, it's a D'Alembert paradox, but there is no paradox at all, in the sense that in an ideal fluid, there is no resistance. But however small friction produce finite resistance. I just realized this is called anomaly. Okay? As a symmetry breaking factor nu goes to 0, effect of symmetry breaking stays finite. When nu goes to 0, this area stays finite. When you increase viscosity, this changes and all the way to the Stokes viscous flow. More questions?
So is there a critical velocity when this opens up?
It's when you start from low Reynolds number, you have a symmetric, almost symmetric flow. About Reynolds number 4, you start seeing a symmetry between left and right, which is always a problem. About Reynolds, depending on whether it's cylinder or sphere, Reynolds 30, you already start creating wake. Okay? And of course, there is a beautiful application of it to wings, because for wing, it depends on the angle of attack. And there is, as any pilot on the courses learned in some hard way, that there is a critical angle in which this, this is called separation. The phenomenon is called separation of the boundary layer and creation of wake. And wings created differently depending on the angle of attack, and many people paid their life of learning what is the angle of attack. It's independent of Reynolds number. I actually consulted people who were doing manuals for pilots, how is the easiest way to explain why the critical angle does not depend on Reynolds number. Yes?
The latest, I guess, golf balls are famous to dimples, but they cause this to come earlier.
Let's talk about it on Thursday. I mean, we'll do all the, there's many things related to it. Look, this is one of the, this is essentially, I mean, look, this is Newton and this is Prandtl, and we're talking about kind of most singular events in fluid mechanics, but the lessons they teach us are really, so let's repeat what did we learn. It's 10:29, so I have 1 minute to repeat the moral, the lesson, right? And then I'll answer your question. What we learned, it's renormalization of mass. That's ideal fluid already teaches this lesson. And then the next thing what we've learned, we started to learn it, it's anomaly. That even tiny symmetry breaking factor in a nonlinear system can make an anomaly. The effect of symmetry breaking stays finite. Last question. Oh, we may continue if Julia would allow us. Yeah.
So according to Navier-Stokes theorem, say symmetry, there is a conservation law. And
Speak louder.
so from Navier-Stokes theorem, where there is a symmetry, there is a conservation law, right? And for anomalies in quantum field theory, once there is a symmetry breaking, there is like a current, like chiral symmetry, there is like chiral current.
Yeah.
And for dissipative anomaly, so what is the corresponding thing?
Okay, so the question was that usually when there is a symmetry, there is a conservation law. On the other hand, if there is a conservation law, we can consider about currents of a conserved quantity. And in quantum field theory, for example, we know how this, the current anomaly, which appears actually by Schwinger 10 years later after Kolmogorov formulated the dissipative anomalies on turbulence. So what can we translate one phenomena into another? I'll talk about it on Thursday a little bit. But generally, I hope you'll be around on Thursday. Yes? But generally, it's very similar. So in a sense that anomaly always comes when you cannot satisfy two conservation law together, you need to sacrifice one of them. And friction, something which conserves momentum, but it doesn't conserve energy. And for example, for chiral anomaly, and again, if somebody didn't hear about it, I'm not doing any explanation now, is also you need to sacrifice one symmetry to preserve another. There are many different and deep analogies. Polyakov was the first from whom I've heard that what we know is that the resistance of the body stops depending on viscosity when viscosity is very slow. It's the same thing which anomalies in field theory. And I don't think maybe Polyakov was the first who actually realized it some, I don't know, 20 years ago, that we're talking about the same phenomena. But Polyakov always says that he was sure that Kolmogorov knew it, but he never, okay, but that's historical. Yes. Julia, are we going for so?
No, that we can carry on.
Just in terms of this picture, so in the limit of vanishing viscosity, the difference between volumes or areas on the two sides goes to a finite number R squared?
Yeah,
That's
F.
what the statement is.
Yeah, the statement was that when viscosity goes to zero, this point of separation fixes. It just stays here, and the resistance is essentially this area.
And it's just determined by the radius, by the size of the object.
Yeah, R squared, and the geometric factor, the C factor, which comes here, is essentially this ratio to that ratio. Okay?
But is that ultimately coming from the UV cutoff on the sort of molecular scale?
Yeah.
That's really...
Well, no, it comes out of viscosity. Viscosity is determined by mean free path. It's a molecular quantity, right? It's a diffusivity which comes out of molecular motion. Yes?
I guess this is back to your symmetry discussion of viscosity. So people talk about an odd viscosity, like addition, like you also, when you have time, well, they say that when you have time reversal, you don't have this component. Then when you break time reversal, this component is allowed to appear. But then if I look at pictures like the one you're drawing, time reversal is broken in such a system. So what is meant?
Okay, good. So let me repeat the question and also a little bit reformulate it. So the question was, what is odd viscosity? And because you did not define it, and in a moment I do. And how it's related to time reversibility. There is a following statement, which we use this. What I say is that when you have rotation, namely you can locally have vorticity, it cannot produce tangential stresses. Yes, it's true. But then you can say, okay, but this rotation can maybe produce normal stresses. Namely, imagine that you rotate something and it pulls or pushes down, okay? It can happen in a media like something with magnetic field or rotation. But what magnetic field does, it breaks time reversal, but not in this irreversible way of producing dissipation, but just breaking time reversibility in a sense that this way it rotates Z and that way it rotates Z, okay? And so indeed, in a magnetized media, on a rotating media, you can have another term added to viscosity, only in 2D. Because only in 2D you can have this trick, you know, of like uniform rotation. And it's a beautiful piece of hydrodynamics. You can find it in Landau-Lifshitz. It's an old stuff, not new. But Yossi Avron and Technion wrote several beautiful papers, and now people exploit it. Okay? But it's relation between rotation and non-tangential but normal forces. Okay? That's what is odd viscosity.
So probably I missed this point, but you say even if nu tends to 0, the separation point is fixed.
Yes.
So how do I see this?
No, it's incremental fact. Nobody, so the question was, how I know that when nu goes to 0, this separation point stays here. First of all, nobody computed, this is some angle. For spheres, there is some angle, like, you know, if you compute it, you get Nobel Prize. I doubt it, but anyway. Nobody can compute it, right? It's really, you need to solve flow everywhere. We know experimentally, up to Reynolds number 10 to 7 at least, but also we know experimentally that the force stays constant in the limit. And force, just by conservation of momentum, what comes here, and there is a deficit of a flow here because of a wake. So resistance is essentially wake area, and resistance stops depending on viscosity. When viscosity is very small.
At what Reynolds number viscosity start to play a role on this drag force for a sphere?
As I said, it's easiest to look at it from a very low Reynolds number. So you have a very low Reynolds number, you have a very symmetric flow. Then you start increasing velocity, you decrease Reynolds number kind of, and then around, you increase Reynolds number, so around Reynolds number 4, you start seeing asymmetry between left and right, but there is still no separation. For a sphere, separation is something like 30 or 40. But then it starts doing beautiful things. This separation is first is a very, very regular. Then vortices, is called Kármán vortices, start to appear. Then this vortex street started getting turbulent. Then what Eiffel found after, or before he built Eiffel Tower, he did experiments and he found a drag crisis, which means that around Reynolds 10 to 5, what you find out is that this wake dramatically shrinks like by 30%. And what we now understand is when you make this wake turbulent, it's actually more stable. It can continue further, right? Because it entrains more fluid from outside and have more inertia, and this separation happens lower. That lowers resistance. Soccer players can beautifully use it. You can kind of send the ball over goalkeeper and then it dives down. Because when it slows down, its Reynolds number slows down, its resistance increases. Or if you increase velocity, its resistance drops. It's called drag crisis, it's 10 to 5. It's a lot of things happening on the way to infinity, right? But at Reynolds going to infinity, it stays constant, or so we believe.
Okay. So I think that's all the questions for now. I'm sure there'll be loads more later. Thank you very much.
We tried to rectify a few things. I
No,
hope
lovely,
it
lovely.
went
I'm really
better. Yeah.
enjoying this.
People ask questions on the way. And,